Okay, welcome to the afternoon session. The pleasure to have here Wojtek Chacholski from Stockholm. He has done work both in pure and applied topology. And today he's going to tell us about homological algebra and persistence.
Yeah, thank you for the invitation. It's a really pleasure to be here. I have a lot of Italian connections, and yeah, so it's my pleasure. And I'm speaking here on behalf of the TDA group at KTH. This is a current content of that group, and the people in bold faces were more directly connected to what I'm going to tell you about, but all these things were also part of the discussions of the entire group. And when I was coming here, I was thinking whether I should tell you about applications or be more mathematical, and I made a conscious decision to tell you about mathematics. Okay? We heard some great talks about very particular applications, and I have a feeling that my objective is to show you that there is some interesting math in TDA. Okay? Interesting according to my judgment. Okay? My opinion is interesting. Okay? So I will also try to remind you, give a lecture about homological algebra. I don't know how many of you took a course on homological algebra. We revisited this what homological algebra is. So over decades now, and across many areas of mathematics, people find it convenient to encode information in terms of functors indexed by posets with values in vector space, finite dimensional vector space. That's quite, we can see it over and over again across many areas in mathematics. Okay? Also in TDA, we like to express our observations in terms of such representations. Okay? And we even have, in TDA has its own naming, they call them persistent modules. And these different areas have different reasons why they find it convenient. Okay? I try to tell you today why I believe TDA finds it convenient to encode the work on in this form. Okay? So in TDA, maybe also I should sort of point out that the common posets that people are interested in are natural, finite natural numbers, finite poset of natural numbers, or maybe they are products or Rn, etc. Okay, or maybe not negative real numbers, take the product. Okay, but, so one reason I believe TDA is interested in this, and I would like to make a case during this talk, is that this category has homological properties, interesting homological properties that we can take advantage of. And that's not only why TDA is interesting. There are many other areas of mathematics that like to encode information in this form, because then maybe the homological properties of these objects can reflect what they've been studying. Okay? Same thing happens in TDA. And there's a growing work. The growing work. This is just I took 3 papers from top of my head. There's a growing work in TDA in this direction. Okay. They look at homological properties. Maybe they don't phrase it that way, but they look at homological aspects of these persistent modules, of these representations, and they discover that these homological properties, can be useful in analyzing data. Okay. All right. So, but also I have to sort of another point that I would like to make during this talk is that studying representations of posets in finite vector spaces. This is a subject that's been really traditional and all. For decades, people have been interested in this. So the natural question is, so what's new in these articles? What is it that the TDA suddenly discovered that has not been discovered before? Or maybe we rediscovered this thing and just changed name, give different names to it. Okay? So I think we actually, I would like to point out that we actually have found something new. Okay? TDA community has found something new, but it is not. I mean, it's rather elusive. I would like to sort of make point of what I believe it's new and has not been regarded before. Okay? So in TDA, one of the objectives of TDA is that it's to produce this need of wealth of invariants. That's the whole thing about TDA. We assign invariants to various objects, invariants for system modules of this way to represent data sets, which are these invariants. We want them to be computable. We want them to be able to calculate them. We like them to be stable in various ways, and we would like them to be amenable for statistical analysis. So, and I don't care, that's whether we use homology or not. We need machines to produce these invariants. Because then if we have such an invariant, we can apply them to various data sets and see, does it see a difference between, that protein and that protein? Does it see a difference between cases and controls? All right? Maybe these invariants are in a way that we can feed them in machine learning methods, okay? Or apply them for some, other statistical reasoning that we can come up. Okay? So TDA doesn't care about homological properties. We need this wealth of example. It just happens that most of the invariants people come up with are actually homological in nature. All right? All right. So that's an introduction. Let me start the lecture now. It's a crash course on homological algebra. How many of you took homological algebra? If I ask you what a homological algebra, what you think homological algebra is about, in principle, I'm not giving you an opportunity to answer that question. Tell you what I believe it is. Okay, the slogan is that homological algebra, in principle, is about approximating objects by direct sums of chosen objects. I'll try to sort of tell you why I think homological algebra is like this, and I will go through very classical way of setting up homological algebra. Okay. So the starting point of this thing are these chosen objects. So we choose a collection of objects. Okay, you choose your collection of objects. Okay. Now we then introduce names, right? Whatever we name, there are so many things, but what objects we name, we think are important. Okay, so we name. We name finite direct sums of elements of your chosen family. We call it free. Okay, P free. Okay, this is with respect to that family. Okay, we are interested in free objects. Now, of course, there are situations depending on your family. Representing elements as direct sum may not be unique. There could be many representations. So we need to introduce new case. We say that this collection is independent if for every free object there is a unique function such that you can write that object as a direct sum of elements in A. Okay? So if this happens, if I actually have a unique representation as a direct sum, then this function just gives you the multiplicities of the object. I call this thing independent. Okay? So I'm interested in independent collections. Okay? Independent collections where these multiplicities are often called Betty numbers. Okay? Betty numbers. So we're interested in collections which are independent. Yeah, those are called petty numbers. So now what can we do? What can we do with such a collection? How can we study such a collection, independent collection? So we choose a collection, and this collection leads to things that homological algebra focuses on. It leads to exactness, projectiveness, and acyclicity. Let's just discuss these three notions. So we say that a sequence is exact if for any of my element in my family, if you map this element to all these elements in the sequence, you get again an exact sequence now of abelian groups, or maybe vector spaces, whatever set your setting is. Okay, this sequence of abelian groups has to be exact. Okay, and if that happens, then you call this relative exactness. Okay. Now, once you define exactness, you can define projectiveness. So, what is a projective? Projective, an object is projective if for every exact sequence you map that object into that exact sequence, you get again an exact sequence. Okay, so once you choose a family, you can define easily to the notion of exactness, which in turn leads to the definition of something being projective. Okay? Something being projective. So now an example, a typical example of a projective object is a free object. Every free object is projective. Okay? Now the other way around, it's not the case. In fact, most of my mathematical life, I was interested in cases in which not all projectives were free, and in fact, I was interested in understanding how more projective there are over the free objects. Okay? That's I spent entire my life, almost mathematical life, on. I thought that was the interesting case. But it turns out that there are interesting cases, and I give the name, and that's what TDA deals with. So if the other one, so this is the case that I thought in the past was trivial case, easy case. If every P projective is P3, then P is called a cyclic. Okay? That was like in the past, I would almost ignore that case. I would sort of associate it with, oh, that's an easy case. Okay? But it turns out that TDA, there are interesting cases, there are interesting collections which are acyclic. Right? And somehow this K-theoretical issues, they don't occur for this example. This acyclicity gives us quite a lot of freedom for assigning variance, interesting environment, calculable environment. All right, so you choose your collection. Maybe it's independent. There's a unique representation as a direct sums. Maybe this exactness, which leads to exactness, which leads to projectiveness, and I'm actually be interested in every time it's a cycle. Okay. So now once you do that, once you choose, let's say a cyclic and independent collection, okay, you can try to approximate. Your objects. So you choose an independent. Okay, we have a unique representation of direct sums, an acyclic collection. All projective are free. Okay. So now you try to approximate. So the way you can do that is you look at. So here's a basic question. You might ask the following: is M a direct sum of elements in P? Which means, is M free? Okay. So how would you approach that question? One way of doing this is that, let me look at all possible free objects that map onto M. But exactly, in a P exact way, in this relative way. So I'm looking at these. So whenever I have such a thing, I call it a cover. Okay. Now, among these covers, you might ask, is there among all these covers, all these maps from 3 to m, is there any special object? Is there some very, very special approximation? So one of the special objects you might say, oh, is there maybe a terminal object? A terminal object means it's the closest free object, right? It's the closest, the one that every other maps to. Now, to assure that, there are very few situations in which there is such a terminal guy. Okay? What you can actually, what is much more reasonable to expect is to ask for minimality. I will say that such a cover is minimal if every endomorphism, whenever you have such an error, every endomorphism is actually an isomorphism. It's a typical definition of a minimal object. So now, if you have such a minimal endomorphism, then it's actually unique. Two minimal p-covers are isomorphic. Okay? Maybe not uniquely, but they are isomorphic. Okay? And if you can construct that, you have an approximation. In fact, now, such a minimal cover leads to invariance. Right? You look at this minimal cover, because this collection is independent, I can write this free guy uniquely as a direct sum of elements in my chosen collection with some multiplicities, of course. And so first of all, minimal cover. First of all, by acyclicity, I know that it's free, and by independence, I know I can write it uniquely as a sum. So a minimal p-cover leads to invariance. Every object n gives you this invariance. Okay? So Betty. This is called zero. And this cover is actually a very good tool to detect if your object is a direct sum of your elements. The n is P3, so it's a direct sum of your elements in your collection, if and only if its minimal p-cover is an isomorphism. Okay? So if this is an isomorphism, it is a direct sum. You have a decomposition into a direct sum of elements in P. If it is not, you might study its kernel. You might study how that homomorphism differs from being an isomorphism. Okay? How it differs from being an isomorphism. Now, how do we actually measure the fact that this may not be an isomorphism? What is the tool in homological algebra that we do? We take resolutions. So we don't stop at the cover. So again, choose an independent acyclic collection. The p resolution of n is not just a cover as we had before, it's the whole sequence of elements which are in each degree, which are p-free, because things are cyclic, being free and projected makes no difference. And again, I can think about a resolution to be minimal. And a resolution is minimal if every endomorphism is an isomorphism. And again, if you have a minimal, and again, as before, two minimal p resolutions are isomorphic. And again, so what we do, you try to check, is this an isomorphism? If it is an isomorphism, this is already its minimal resolution. If it is not an isomorphism, it has interesting kernels, so you proceed. So having this resolution encodes how far your object M is from the direct sum of elements in P, from being P. And now, if we can find a minimal P resolution, then we can, first we use acyclicity to know that each layer is free. Then we use independent to write each of those three guys uniquely as a direct sum of elements in my P with some multiplicity. I get the whole sequence of invariants. Okay? Whole sequence of So these two conditions, being independent and cyclic, and having so you see, I so far I didn't tell you under what circumstances such a resolution exists. Okay, but if you have a collection which is independent and cyclic, for which a resolution exists, you can define these environments. Right? You can define these environments. So now the question is how to calculate the obtained invariants. Okay? We want to have invariants. We want to construct a slew of invariants that are calculable. Okay? That's a key, one of the key objectives. Okay? So, all right. So this is the end of crash course on homological algebra. I don't know how it rings with what you've done before. But let's look at an example. Let's look at an example that you might be more familiar with. Let's look at the standard homological algebra on these representations. Okay, on these representations. Okay. So I just for the sake of it, I assume that it's finite. If this is infinite, then you have to assume certain tameness, etc. But let's just for finite for the sake of it. And now I have to choose a family. I have to choose a family of objects. Okay, a family of objects. So the family I'm choosing consists of. So I have to choose a family of functors. So I will choose the three functors on one generator. Do you know what that functor is? You choose an element v in my poset, and this is a functor that is one-dimensional for any w which is bigger or equal than v, comparable. V bounds it below, and it's zero afterwards. Okay, so it's a free functor on one generator, and I consider that collection. Okay, I want to do what I just described you for that particular collection. Okay. Now observe that I can identify. It's one thing I can identify that collection with actually the poset I. Right. Each of these elements of my collection is determined by this v. Right. Determined by v. All right. So the standard homological algebra course that you might have taken can be summarized as follows. S is independent. That means that if you write something in the direct sum of those guys, this direct sum decomposition is unique. This exactness with respect to this is the standard exactness. All right. S is acyclic. All projective are free. Okay, all projective are free. And moreover, all representations admit a minimal resolution. Okay, a minimal resolution. So in other words, if you choose that family, this is a standard family. Each n you can spew the sequence of invariants. Okay, sequence of. So now, how do we calculate the sequence of invariants? We do. So the first one is very simple. What do? You take m and you divide it by the radical of m. So you take this is a functor indexed by I. So what is the radical? It's sort of very easy. You take this functor m. Let's say it's some element v, and you look at the sum of the images or maybe like this, mw for w strictly less than v. And all of those map into this, and the radical is the image of that. Everything that comes from before v, strictly before v. That's the radical. So you take that quotient. Now this quotient is a very simple, it's a very semi-simple module over I, because all its transitions are zero. Okay, all the transitions, because you kill everything that comes before, so the quotient and all the transition are zero. So this is, and so anyway, you calculate this and you look at the dimension vector of that particular semi-simple module. And this turns out to be this zero vector. And now how do we construct higher ones? Well, once you know B0, you know how to form C0, because this is just the sum. I have this. I know multiplicities of that, so I construct C0. Now here is something very difficult to do algorithmically. Once you have C0, you have to choose this map. And there's not a unique choice. There's actually the whole space of choices. So, but you might choose it. And then you do kernel and you repeat the whole thing. Okay? Take this kernel, take the radical, take the dimension, and take 0, and you continue. Okay?
Why is choosing such a bad thing?
Like no, it's not a bad thing. It's very hard.
Ah.
I mean, I would love to have it, but I don't think there are even, you know, first of all, there's not a unique choice. Okay, not a unique choice, and I don't know how to make it effective.
Oh, so it's not about there not being a unique choice. It's about generating any choice.
It just getting up. It's difficult. Okay, and I would love to do this, and I know that we cannot. There's no fast algorithm because it would lead to strong conclusions. Okay, there's no easy fix for that. Okay, so this is a standard way of calculating these things by B0. It's easy. That's easy. Constructing this, finding the map is a trouble. It's not bad. It's a trouble. Okay, finding the kernel, you Gauss eliminate. Doing this, it's also relatively simple. You calculate B1, but then you have to remember what you have to do. Then you have to again do the same thing. You calculated B1. You know how this is done. You know this. So now you get the matrix between three guys. You have to find that matrix, and that's expensive. And you take the kernel and you follow the radical. The trouble of that thing is that it's costly. It's expensive. It is, people do it, why not? But if you actually give a big module to this algorithm, you fail very quickly. Okay? So we have, so the standard way of producing sort of, requires constructing differentials, and they are kernels. That's differentials is the issue. However, there is this miracle. So now I'm continuing the standard homological algebra. I hope you will remember or connect this. There's this miracle. Miracle happens, and there's for certain I. For certain I, a miracle happens. That I can construct these numbers without having to construct these differentials. Okay? And the magic of this is the slogan is Koszul complexes. Okay, Koszul complexes. But you have to, you know, in order to do this, you have to assume something about your poset. You cannot, Koszul complexes do not calculate what you want unless your indexing poset is special. And that special means assume it is an upper semi-lattice. So what it means,
it has to be an upper semi-lattice, or there are other situations. So it is necessary.
No. There are other situations, absolutely other situations. Okay? But they're individual situations that you can do. First of all, there are some local. I do it because it's so easy to phrase. Okay? But you have to assume something about I, and so I don't know whether you know what upper semi-lattice means, but this means that you see I is a poset. So I is a category. So in a category, you wonder, can you form a coproduct? Okay? So if you can perform coproducts, this is exactly upper semi-lattice. Coproduct of non-empty subsets. Okay? If you can perform coproducts of non-empty, if you have two elements, you can perform a coproduct, then this is upper semi-lattice.
What do you call a coproduct?
It's a coproduct. No, it's a coproduct.
A categorical coproduct.
categorical coproduct in the spot in the category in the positive category. So, okay. All right. Exactly. Okay. All right. All right. So here I should maybe use coproduct. I like coproducts. Those are the names that combinatorials can use the word for it. So now once you have this, and actually the condition that you write, you don't even need. Okay, you'll see. Once you have this, I will define a Koszul complex at a given element V. So I choose my V in I. So you can, by choosing V, do you remember I identify I with my chosen collection? Okay? So I can think about this V as an element of I can think of it as a free functor in that degree. Okay? And here's the way I define my complex. I take the value of my functor at V. Then I look at the subset of one element subset, which are bounded below. So for one element subset, all element subsets are bounded by itself. And I take the meet, the product of that element, because it's bounded below, the product exists. In this case, because it's one element subset, this is just this S itself. And take the value at these products. Okay. Now I move forward. I look at the two element subsets that are bounded below. So I assure that there is a product in that category. I take the value and I continue. Okay. And you can imagine that this is with a standard differentials where you forget the alternating sum when you forget one of those elements. Okay. When you forget.
What's usually
so okay. Right. This is set of parents. So you look at V, this is your poset. You look at the guys that V covers directly below that element. Okay? The guy who just sort of, one step back. Okay? So sorry. You look at the set of parents of V, depending on the cardinality, take these products, and you form this sequence of that, and then it's a standard way to show that that's a chain complex, because take alternating sum, this is a standard thing, and here comes an amazing fact. Like, observe that this has not, this doesn't involve any inductive step. I know something about V, I know something about its parents, and I know how to form products of subsets of its parents. It's a very local information. Okay? And this statement what I make is true every time you can do that. Every time this product exists. So this product exists, for example, in the case of an upper semi-line. Now, the key statement then is d beta number, this beta at that V, is the dimension of the deep homology of that complex. Okay. Right. That's the beauty of the Koszul complex. You don't need to find these resolutions. You don't need to construct these differentials if there's some interesting local properties of that element V. You write this explicit chain complex and you calculate its homology. Now this is chain complex of vector spaces. There are very fast algorithms to do that. That's really no-brainer. Even if n is very big, we just look at what happens. This is very calculation. And the fact is, and that's that's the end of the crash course on homological algebra. That's typically somehow the mathematical height of standard homological algebra course that I grew on. Okay, this Koszul complex. Projective, the multiplicities of these in the multiplicities of this free module in degree D can be given by the dimension of the homology of the expression. Very calculation.
So what is cardinality? Is the bars indicate cardinality?
Yeah. So this is cardinality. This is one element sets, subsets of the parents. So in this case, this is just the parent, that's the element itself. Okay. This is two parents. So you see, you have three parents. So in this case, if that's V, and you have, let's say, P1, P2, P3, you take M, V, then you take the sum N P1 plus N P2 plus N P3. And then the next one, you have to have pairs, and you want to make sure that these pairs, it's bounded below. Once it's bounded below, you take the product of those. Okay? And then you take the value of your function on this product. So at the end, what you do when you start performing this product, that looks like a cube. It looks like a cube. You take this product will go this bigger and bigger size.
Yeah, how do you construct the maps between
these maps,
yeah.
these differentials?
Yeah.
This is the usual one. You take a set, you forget one. Okay? You forget one, and then of course this guy sits below this other one. So this is the transition function. Okay, take alternating function. This is a standard one, forgetting. All right, the next one is empty. I don't know. Now, I just finished the crash course on standard homological algebra. So you might wonder, what if I took some other collection of objects? Okay, other P. Why should we do standard? Okay, why should I standard? So it turns out that in order to use Koszul complexes to calculate these P Betti numbers, because that's what I'm after, P Betti numbers, I need additional information. I need to be able to phrase these assumptions that I had before about this upper semi-lattice, etc. Okay? So what I need grading on my family that I choose. This is an additional information that I will be using. So what is a grading? So let's assume that the collection P is not unstructured. There's a functor from some other poset. It's a contravariant functor, that's all. Contravariant called grading. That's a poset, okay? And I'm interested in my collection P is the image of that functor. Okay? It's the image, right?
So for example, the example you described earlier, J was I.
I, exactly. J was I itself. And you said V to KV. Here I'm taking some other J. Now, every time you have such a functor, this is for those people who've never seen that, don't worry. But it leads always to pair of adjoint functors. I can transform, every time I have this, I can transfer from this category that I'm interested in, maybe with the collection P, to that category over J. Okay, over this grading of my new basic objects P. Okay? And so this functor sends M. I'm looking at the image. I'm mapping all these P into M, and this way it goes the other way around. I take the free functor and I'm sending it to that functor that forms my family. Okay? This free functor on one generator is sent to this interesting object that I'm trying to use to decompose other things or approximate other things.
But that isn't fun J to fun I vector.
Say it again.
Is fun J vector or fun J fun I vector?
Yeah, so this is the representation of I, this is representation of J.
Okay.
Okay, so now if you have a functor indexed by I, this is P of something, is a functor is indexed by I, and you look at natural transformation. And now you have this this slot that you can put various elements of J here. Okay, that's why you get the functor from J. Okay. Now, if you have, I'm not telling I'm here in that way L, I'm just telling you where that functor is being set. Okay? L is left adjoint to R. Okay? That functor, if you look at left adjoint, that functor is being set. All right. Okay. So in particular, there's these, every A in J leads to this is the standard map. When you take any functor, you have like left adjoint and right adjoint. There is a map which is adjoint to the identity. Okay. So we have, there's this always, this guy. I know what it is. This is natural transformation from P, arbitrary thing I can stick into this P of L. So I always have this natural transformation, and here is the key observation. I call my P, this grading, I call thin. If that thing is surjective. Okay. So let me just explain what that means. It means that for every A less or equal than B in my coset, in my grading, every natural transformation from PB to it should be PA because it's contravariant from PB to PA. That should be A, is given by transition times some number. Because this has one-dimensional values, so it means that any natural transformation, and if you have one of the standard natural transformation here is the transition, right? So being surjective means that every natural transformation is lambda times this transition. Okay? Once you have that, we call that thing. So in particular, this grading has the property that for any A less than B, natural transformation from PB to PA is at most 1. It's one-dimensional, because this is either one-dimensional or zero-dimensional. Okay? All right.
Sorry. Does this have to do with pre-sheets? Because we are coming from the opposite of a category.
Yeah, but so I'm not introducing any topology. Why would you call it pre-sheet?
No, because you call it grading, and in category, for me, because I'm beginning category theory, this looks to me like a pre-sheet. I don't know why you're calling grading.
No,
It can also be called a pre-sheet, but he's calling it
yeah.
grading.
Oh, okay.
I mean, I actually myself, when someone told I not call those things sheaves or pre-sheets because there's no topology. Sheaf, whenever you have a sheaf condition, a pre-sheet condition, you'll have some decomposition things. Things on smaller guys give rise to.
Yes.
This is just functors. Okay. It's just functors.
First, no, I was getting.
Yeah. No, that's just. So now, let's assume that we have this thin grading. Okay. Then again, you get the same thing. That collection turns out to be independent. Once you have this thinness, automatically the direct sum of these L of such guys is unique. Okay, you have Betti numbers well defined. Sorry, it's acyclic. All projectives are free, and moreover, all functors admit a minimal resolution. Okay, a minimal resolution, and therefore we can do exactly the same thing what we do for standard. With every m we can associate this invariant. I look at this minimal resolution, I choose some minimal resolution, and I count multiplicities of these elements in this direct sum decomposition. So I get describing multiplicities in the minimal P resolution of various elements of my family. Right. So now the question now is, how do we calculate this? So far, so far what I want to argue is that what I believe TDA found is that so far, before TDA, people did not care about thin collections, about collections which are independent and acyclic. TDA has found a slew of examples of collections which are independent and cyclic and for which minimal resolutions exist. I believe that's something new. No one thought before about this. People didn't step on that before. Somehow did not play an important role in the past in mind. Okay. All right. So now the next question was: you see, in the standard homological algebra, we had this amazing fact. We had this Koszul complex. Right? We had this Koszul complex that was very effective in calculating these Betti numbers without the need of describing these differentials. Right? So what happens? Do we have such an apparatus for thin files? Okay. So if this is if this is a standard minimal cover, okay. So what happens? Do you remember we use this grading, what I call grading, to translate? This is the place that I'm interested in, and we use it to translate to find those representations over the grading. Okay? And it turns out that if you choose in that world a standard minimal cover, with the standard, you choose standard minimal cover here. So you start with something M, you translate into this, you find a standard minimal cover that I explained before how to find that standard minimal cover. You get this math. Remember that I can always take the adjoint of that. It turns out that the adjoint is a minimal P cover. So this gives you, for thin functors, this gives you a way of constructing minimal P cover. It gives you a way of telling you whether M is a direct sum of elements in P or not, if P is thin. Okay. That's one observation. Okay. So in other words, this beta 0 can be calculated as follows: of M, translate, take the radical, kill it, find the dimension. It's very calculation. It's very calculation. That's okay. So that gives you effective checking if M is a direct sum of elements in P and describing its components. Okay, describing its components. So now, assume in addition, okay, assume that this is thin, because I need thinness for this, but also assume that this J is an upper semi-lattice. Because if I know that J is an upper semi-lattice, that in the standard world, I have this calculational ability to calculate the standard Betti number. So I know. So here, what I would like to argue to you, is that it turns out that for many A in J, these relative Betti numbers are actually given by the Koszul complex of this Rm, which gives you a very effective way of calculating these relative Betti. I'm not explaining for this sort of many, okay? But let me just finish this by giving you two examples. Okay, two examples. Let's just start with the standard concept that TDA people are interested in, M square. And let's look at. So I have to choose a family of things that I want to try to approximate. Use direct sums to approximate other objects. So I will take lower hooks. So what is lower hook? I choose V and W. W is this outside element, and V is that element. And I take that guy. If you think about this, what these lower hooks are it's co-kernel. You take the free guy on V, you take the free guy on W, and you kill it. But observe that this collection of these persistent modules comes naturally equipped with grading. What is the grading? I look at two elements. My poset J will consist of two elements, comparable elements in I. All right, and I allow sort of infinity as well. Okay, and I'm assigning to that grading. I'm assigning to this pair the co-kernel, exactly that element. And it turns out that P is thin. It turns out that for every m, and it turns out that for every m, I can tell you, I try to resolve this m now not as this resolution is not as a direct sum of 3, but this direct sum of these lower hooks. All right, I do it in a minimal way, and I wonder how many lower hooks appear in degree, in some degree. Okay, what do? I translate this to look at the J. I calculate this. I write this standard Koszul complex, which is very explicit, and I calculate the dimension of the decombination. Okay. So fast and effective way of checking if, for example, M is a direct sum of hooks, and describing its components, for example. Another example is, let's consider the following collection of persistent modules that I would like to approximate other modules by. Those are rectangles. Okay, it's hidden one-dimensional here and it's 0 everywhere else. Okay. Now this comes with natural grading. What is natural grading? It's the same J as before, and I'm assigning to that, the rectangle between V and W. Okay, V and W. And again, P is thin. And again, I know how to calculate. You start with arbitrary m. You write as a direct sum, not of 3, but direct sum of these rectangles in a minimal way, and you wonder how many of them are in certain degree. And I don't want to construct these differentials because it's costly. What I do, I'm translating to that J. I write an explicit Koszul complex. Calculate its dimension, and for that particular element, and it will tell me how many multiplicity of that rectangle in that degree in this approximation. Okay? So in conclusion, TDA has brought a systematic study of homological properties of this relative to, so it didn't bring to systematic study of homological properties. That was done for decades. But it brought the systematic of study homological properties relative to independent and acyclic collections. Okay? These independent acyclic collections, for some reason, people were not interested in this before. Okay? According to me, I don't know, maybe I'm ignorant. Okay? Now, grading such collections by upper semi-lattices enables fast and effective calculations of the relative Betti diagrams using these Koszul complexes. Okay? And I want to sort of say that this is all inspired by these papers by Steve Odo, by Magnus Botnam, and other, where now I forget. I should remember these people, the papers that I mentioned at the beginning. What I was telling you is try to explain, our understanding of their work, and try to see, how can it be extended, how it leads to maybe effective calculations, etc. Okay? That's.
The point is when we have a category of parameters, find another poset J for which the category of parameters.
For which the image, right? For which the image right? So that we want to find thin factors.
Yeah. Yes.
And then if you find a thin factor, that you look at its image, and then you look at the homological algebra relative to its image.
And I was wondering, is there a theoretical construction to construct such P and J, or in every...
No, it's like you look at these examples. When you look at these examples, right, these lower hooks, you know, it is something special. You just find out. You have a family. Remember, one of the thinness means that you have to have a family that natural transformation from any two elements, whenever A is less than B, from natural transformation from P of A to P of B has to be max one dimension. Okay, so they are very special. Okay, and sometimes it happens. Sometimes it doesn't happen. Right? But if this happens, so it's a very special situation. Okay, very special situation. It's, you know, we in our paper that just appeared on arXiv, we give many examples of such families. Okay, and amazingly, you look at these papers of Magnus and this Japanese people, very good paper of Japanese people. They don't talk almost. They all the examples that they figure out are. All the examples that I've seen are thin.
So a key feature is that
this Betty.
Yeah, the natural transformation should be one dimensional.
Max one dimensional or zero.
Thank you.
So, suppose we start with a collection which is like too big. Maybe we have just taken not only rectangles, but maybe also with some lateral strips. So we have too much stuff. Do you think there is some, say, algorithm to like get a subset of independent collection?
Right. So independence is very generic. Okay. If you, for example, okay, I show you lower hooks whenever or this whenever you have they are called spread modules. Maybe, you know, some people have spread modules. If it starts with one point, and here you can have many points. Okay. And they are one-dimensional everywhere. They will be also thin and everything. Okay. The trouble is if you have like this. Okay, several of those. Right. This is an example of not thin. Okay. If the source is one point, okay, then it tends to be thin. Now, but even those, they are independent. Often they are independent. I believe I don't know where. I believe they are acyclic, although I believe they are acyclic. Okay, but typically what's missing is ability to go to. You see, the idea here is that I'm translating. You see, here I'm translating between these and these. And I want to make sure that, and I want to have this relative resolution. And I would say I can construct relative resolution here by taking the standard resolution there. Okay? And that I can do only when the space of endomorphisms of this P into itself is relatively small. If it's high dimensional, then what happens is that you can do such translations, but this J will no longer be a poset. You would say, like, I will have to take endomorphism ring of my P. And that becomes calculationally, it kills it. So you can still find this translation for mathematical reasons, where instead of J, you don't get a poset, you have actually a category with many endomorphisms. That encodes that information that this space of endomorphism between things is higher dimensional. And that creates an issue. Okay. order.
I have a question. Can you do this for n to the k?
Yeah. This is whatever I presented. This I can be any possible. Yeah, that works for n. Of course, higher dimensional, you have more possibility of these families. Okay, and for let's say for n dimensional, you know these minimal resolutions can be quite long. Right? Can be quite long. So that's really gives you effective way of calculating these. You ask, you start with a module, you try to write it up as a sum of cubes, n-dimensional cubes. You fit it in a minimal way, and you ask what is it in this. If you have 100-dimensional cube, you ask how many of those are in degree 80. That gives you a very effective way of doing it without constructing the resolution.
Other questions? Not, let's thank Wojtek again.